Next slide. The reason why we want to have larger telescopes is because larger telescopes have better light gathering power and resolving power. In order to even detect something, your detector needs to have enough light gathering power to collect enough photons to sense something. A bigger objective gathers more light, so to increase the brightness of images, to see faint, faraway objects, you need to increase the diameter of your light bucket. That's why the pupil of your eye dilates at night, as shown in the far right photo. The light gathering power depends on the area of the objective, which goes as the diameter squared. That means to compare the light gathering powers of two telescopes, you need to compare the areas of their objectives. You divide one telescope's objective area by the area of the other objective. For example, how much brighter will a star be as seen through a 51 centimeter telescope compared to the star seen through a 3 centimeter telescope? You divide the area of the 51 centimeter telescope by the area of the 3 centimeter telescope. The 51 centimeter telescope is 17 times larger in diameter, so it has 17 squared equals 289 times larger light gathering power. What does this mean for how far out into space you can see? Well, light spreads out into ever larger spheres, so the light spreads out with the square of the distance. The light gathering power depends on the area equals diameter squared of the lens or mirror, so the square factors cancel each other out. Therefore, the distance limit you can see something then increases as just the diameter of the objective, not squared. A 2-meter telescope can see 2 times farther than a 1-meter telescope. A 3-meter telescope can see 3 times farther than a 1-meter telescope, etc. This assumes that the exposure times are the same. If you leave the shutter of the camera open longer, then you can, of course, collect even more light. The resolving power is the ability of the telescope to detect very small details and produce sharp images. The resolving power depends on both the diameter of the objective and the observing wavelength. The more wavelengths that fit across the diameter of the objective, the more information the telescope has to produce a sharper image. It's like the difference between a picture of something taken with a camera chip that is 1,000 pixels across versus a chip with just 20 pixels across. The 1,000 pixel chip image will be much sharper than the 20 pixel chip image, and the file size will be a lot larger. To increase the sharpness of images, you make the diameter of the objective larger and/or observe at a smaller wavelength. The picture on the right is the Arecibo radio telescope, which needs a mirror 305 meters across because radio wavelengths are so darn long. The next set of 4 pictures are images of the same binary star taken with 4 different sized telescopes at the same observing wavelength of 500 nanometers. The exposure or integration times were set to collect the same amount of light. The 6-inch telescope A in the top left took 30 minutes to collect the same amount of light as the 20-inch telescope B in the top right, which took just 2.7 minutes to collect the light. Telescope C in the lower left corner has the same size mirror as the Hubble Space Telescope, and it took just 7.3 seconds to collect the same amount of light as telescopes A and B. Finally, telescope D in the lower right took just 1.6 seconds to collect the same amount of light as telescopes A, B, and C. Note the radically different resolving powers of the telescopes. The light waves from the binary star have to squeeze through the narrow opening of the 6-inch telescope and therefore get spread out by a process of waves called diffraction. The larger the telescope, the less diffraction there is, and the sharper are the images. The animation of the galaxy M33 shows the views through 3 different telescopes. The 3-meter telescope image is 10 times sharper than the 0.3-meter telescope. An array of telescopes can be connected together electronically to create an interferometer that acts like one large telescope. The resolution of the interferometer array depends on the diameter of the entire array. It is much easier and cheaper to make an array of telescopes than one huge telescope, and it's also easier to cancel out signal contamination from Earth-based sources like microwave ovens, garage door openers, and cell phones. Radio observatories were the first ones to exploit the power of interferometry because they were forced to do so due to the very long wavelengths of radio waves. Each radio dish of the very large array is 25 meters across, and they are placed on a Y-shaped track, which can separate the telescopes so that the array's diameter is up to 36 kilometers across, which means it can have an equivalent resolution in the radio band to a single dish 36 kilometers across. And since it's just electronics, we can connect radio telescopes across the Earth to create an Earth-sized telescope such as the Very Long Baseline Array and the Event Horizon Telescope. Magnification is the least important power of the telescope because it simply enlarges what the telescope already sees. A small fuzzy blob becomes a large, fuzzier blob, and the contrast is less. In the next slide, we'll see that the Earth's atmosphere can make highly magnified images too noisy or blurry to use. In the lecture outline, there's a line that says, "Views with radio eyes, if time permits." That's the fourth lecture slide, so I'll save that for later.